So, there's one, today is totally about going into other Python libraries and NumPy, SciPy, talking about what these things are, why they're useful, and why they're exciting. Not necessarily learning as much specific, like, here's how you do a thing, more in the vein of, okay, I've showed you a little bit of Python, and we know a little bit about how to get started in Python. Maybe not a ton, but enough that hopefully you should be able to pick things up, talk to your friends, talk to people who might know Python, figure stuff out. This is about talking about what tools exist that once you get to that point, you can go even further and you can get some really awesome things built. To do that, I first need to cover one or two features that are important for some later development we're going to do. This is just reading from a file. So Python is one of the easier languages to do this with. If you've ever worked with C or something that has C-like syntax, reading from a file in C is hard because it doesn't take care of this magical buffering stuff. With Python, we can just ignore it. We can say open a file with a file name. R is for reading. You can also do W for writing. I think you can also do RW for read writing. You can do B for buffered or byte. I forget what B does. I've never used it really in any way that matters. But you can then write a for loop where you say for every line in the file, do something to close the file. The reason this matters in the end is that later on we're going to talk about how you can persist data and the idea that if I run a simulation, I may need to save data to a file in order to be able to access it or run other simulations or even just, oh, I need to count things, whatever it may be. As I said, writing to a file, you change this to a W, and then you want to call, this is your file, it's open, you have a pointer to it somewhere on the disk, and you just pick stuff to put in it. Simple as that. You can write objects, you can write strings. We talked about this last week, we'll talk about this later. Cool. So that was the end of last week's presentation, and here is part 2. If I can remember how to start a slideshow. Hey, the date's changed. That's exciting. For those of you who filled out those surveys, thank you. I appreciate that. I like knowing what I'm doing good and bad. But I also like knowing what you want to hear about. So I got 3 real requests. Somebody wanted me to go over batch files, someone wanted pickled variables, and someone wanted NumPy. Batch files is a huge topic, and I'm really not going to be able to go too much in depth with it, especially because it is really kind of off course from where we want to be. A batch file is the script that is actually run by the operating system. So in this case, Windows or DOS, or you have the equivalent in Mac and Unix land, which are shell scripts. Batch files typically have the .bat suffix on them. Shell scripts can have .sh, .bash, or no. There's also ZSH, pretty much anything with an SH, because that stands for shell. So the purpose of a batch file, I'm going to go to that, next slide. Essentially, we can automate tasks and we can call our programs that we wrote. So an example of a batch file might be, this is an example we use in the one class. We actually make students implement it. So we have a bunch of files that we've imported that are music files. And we have them in the format of, let me just start typing this so that way you can see it rather than just hear it. Is this text too small? Way too small. Forgot about that. Thankfully, I remembered where that setting is. go. So let's go into Python. So we might have a file in the format artist-song.mp3. So your artist could be Led Zeppelin, Tom Petty, whoever you want to listen to. Your song, pretty self-explanatory title of the song. If you want, we can even make it a little more challenging and have something like album, if I can spell. Album name song. And what we might want to do is we might want to, instead of having these all in one folder, where we have, 1,000 songs, or 10,000 songs, or 100,000 songs, however big your library is, we might want to break it up so there's a folder for each artist, and then in that folder, there's a folder for each album they have, and then all of their songs are in there. So a shell script, if I want to write that as a Python script, it's kind of frustrating because I'm going to have to look at each file. I'm going to have to use some system commands that aren't really, I don't want to say they're not good, but in my opinion it's easier to just use the commands that are already in the shell or in the operating system rather than use Python's interface to those commands. I'll have to break up this file name, rewrite new files, copy things over, and it's a little bit of a hassle when the operating system already has those tools built in, and I can just go straight for that. So that's one example. There's a lot of examples where you use a shell script. An example from my one job, when you have an Android phone and you want to install an app to it from the command line, there's a tool called ADB, Android Debug Bridge, and ADB has a limitation, which is when you tell it to install, it's ADB install and then a APK, which is the program, the app. When you tell it to do that, it will only install to one phone at a time, which is pretty stupid, personal opinion. We have another command called ADB devices that lists the device ID of all the phones. We can strip some stuff out of ADB devices, pipe it into the install command, and that will actually install on every phone. So that's one example. It's a really small thing. It's not a huge deal. It doesn't save you, an hour. It saves you like 10 seconds, but every time you use it, it saves 10 seconds. And if you ever do mobile development, sometimes you're reinstalling things constantly. And sometimes, depending on what it is, you might need one phone, you might need 10. My work, we were using about 3 or 4 at a time. So, anyone ask about batch scripts? Is that anyone in the room? Do you have questions about it? Does anyone else have questions about batch scripts? Because this is really all I'm going to talk about with them.
I was at least one of the people who asked about batch scripts.
Okay.
And so I was wondering, since Python is an interpreted language, I didn't think you would have, I wasn't sure what you would use them for in principle.
What you would use a batch script for?
Yes, since you don't need to compile a Python program.
I think I might be a little confused on your wording.
Okay. Well, never mind.
Okay.
Basically, what's the general principle? When would you use a batch file?
When would you use a batch file as compared to something else?
Yes.
Batch files, I guess, are best used for operating system dependent code or operating system commands. I'm not going to be moving files around with Python. That's more work than it's worth. If I have, I'm going to just show an example. I have all these files, so I've got useq.java. It's some Java file I wrote for an interview. Let's say I don't want it in the folder it's in. If I want to move that in Python, I've got to do some kind of, I don't even know how I would do it because I've never considered trying that. But I'll have to do some kind of weird loading and saving and not worth it. What I can do instead, and I think this is the same for a Windows machine, is I can just say move my file, and then where do I want it? Let's say I want it in the temp folder. And it works. If I look in the current directory, use Q is gone. If it was in here, it would be right here, because it's alphabetical. If I move into the temp folder, and I list the contents in here, it is in fact right here. So I guess, making sure I'm in frame, I guess that batch files are used for operating system code more than general purpose things. You can use Python to accomplish those same tasks. I've never wanted to. I've never wanted to figure that out. Batch scripts are also nice because we can do things where, so this will search files in the current folder. Actually, let me check something real quick. Pattern file. So this would search all files in the current folder for the string Q. And we'll see that it's really only used in this one, in these locations. And then we can then save that to a file. There's all kinds of things that you can do in a batch script that are just easier in one line, but it has its limitations. For example, one of the most common Unix shell scripts right now is Bash. By itself, Bash doesn't have support for floating point numbers, which is a huge limitation for a programming language. So they're useful for a lot of things, shell scripts, but I guess they don't cover everything. And part of it's also preference. I can write programs in Bash, or I can write them in Python, and they'll be functionally equivalent. I'm just putting this back. And, okay. So, as I was saying, batch files can do these things. Somebody asked about pickling variables. Anyone want to admit to that? Okay. So, pickling a variable is the same as serializing, marshalling, or flattening. They all mean the same thing. Pickling is writing an object as a byte stream to a file. And that sounds a little confusing, but this is why we needed the file tasks. Essentially, the point of it is, if I have some data that I want to save, I can write a custom routine for it and say, okay, open a file. On the first line, write the name property of the class. On the second line, write the class, the room location. On the third line, write the snacks available. On the fourth line, write this next thing. And you have to deal with maintaining this. Let's say I have some data type and I add an attribute to it. I then have to change how I save it and how I load it manually. Pickling takes care of that for us. It lets us just say pickle.dump our object and then where, like what file to put it into. And as long as we can save data that way, we can load it this way. There's a pickle.load and then the file and then like where to put it. So that's what it's used for, just persisting data in a easy and hands-off way. Good? Cool. In addition, pickling, I've never worked with it too much, to be perfectly honest. But essentially the rules are you can pickle everything unless it's an object that is not on the top level of a module. And the exact meaning of that, once again, is lost to me because I don't use this very much. So if you are interested in that, I'm willing to assist in learning, but I actually have never worked with an object that can't be pickled. My next request was NumPy, and this is really cool stuff. So I found a pretty good example I like online of using NumPy, and I'm going to kind of click over to it, and then I'm going to show you the highlight reel of it. And Firefox, I didn't really want you. I have it open. Mind the swear words. I apologize for my friend's poor vocabulary. Nah, just kidding. All right. So, do that. Cool. So, this person, apparently who's French, I don't know, they have a French URL. The .fr is kind of a giveaway on that. They use Conway's Game of Life. Do you guys know Conway's Game of Life?
Yeah.
Okay, well, I know you do. Conway's Game of Life, I'm going to show an example of this in a second. Essentially, it is known as a cellular automaton. And there's a two-dimensional, the conventional game, there's a two-dimensional grid. I'll bring it up, because this is a better way to show it. And there are a couple different rules describing when this is just a Wikipedia article. Is this big enough that you guys can actually see it, or? Yeah, mostly, pretty much, kind of. I'll make it a little bigger. So we have cells, which are known as each of the individual squares on the grid, or what they are known as. And there's a few rules. Every cell has 8 neighbors, so the one's just creating a box around it. A cell that is already alive has less than 2 neighbors, dies, caused by underpopulation. A cell with 2 or 3 live neighbors lives. A cell with more than 3 live neighbors dies, overcrowding. And a dead cell with exactly 3 live neighbors becomes a live cell by reproduction. So we can see a big little example of this. This one's known as a glider gun. We essentially have these little blocks that are 2x2s, which is a stable because if you look at it, one block has 3 next to it, which means it stays alive. This block has 3 next to it, so it stays alive, etc. And we have this contraption that moves back and forth, kind of does something but returns to a stable position, and they shoot off these new little creatures that move. These are known as gliders. And this is actually, the reason I'm going over this is what our example uses. The exact rules, nobody ever does this by hand. It's always pretty much simulated because you have to figure out each of these steps. New piece of paper, okay, next, and it's just way too time consuming. I got a couple examples of this that I'll show you. This is the one you already saw. This is that on a larger scale, where what you can see here is this is a self-contained version. It's kind of spitting back and forth at itself. And this is not self-contained, it's launching these gliders somewhere else. Let's see what else. This is really big, and I have no idea what they're even trying to do, but they're kind of doing some stuff. Looks like it spits things out here. And then eventually launches these. Who has time for all of this? No idea. That's the takeaway from this. If you get into this one's actually really cool. This is the ALU from in a computer. I don't know if this is an ALU or just a piece of it. I think this one's a full ALU because I've seen this example before. But each of these I think represents like 1 byte in memory, or 1 bit, I'm sorry. Again, don't know who has this much free time on their hands.
Are they creating these shapes by applying those rules?
Yeah, it's just those 4 rules.
How do they start? Is there
There's an initial state.
Okay.
There's some initial state, and then you just keep applying those rules, and it does some crazy stuff. If this interests you, I totally recommend you look at it.
I know the Game of Life. I don't see something like this.
Yeah.
Homework.
There's different rules about things that like rotate. There's different constants. There's repeating patterns, all kinds of things. And it's, I think, of some interest to mathematicians. I'm not actually sure who really does a lot of time studying this. We looked at it in some artificial intelligence classes. Golly, golly, golly. All right, so I'm going to stop showing random examples, and we're actually going to look at the Python stuff that I want to show you. So, in this guy's example, he starts out by explaining the game of life. So even if you're not doing this with me, if you just look at this site later, he shows you all the details. And this is a single time evolution for a glider. So it shows that with one step, this piece becomes alive, that one dies, that one dies. On the next step, yeah, it moves. Moral of the story, it moves. Now, we're going to represent the game in Python as I'm going to make this bigger again. A two-dimensional array. So a two-dimensional array is just an array of arrays. Everybody kosher with that? Everybody cool? It's good. I'm getting blank stares, but I don't know if they're blank stares of acceptance or of defeat. So the ones in this section are the pieces that were the colored dots in the previous one. So I think it's upside down from it, but it's the same thing if you look at it. Yeah, it's upside down. It's just a flipped up version of this one. And this person wrote a function here, compute neighbors. That compute neighbors will determine how many living cells are next to a given cell Z. No, it does not do that. It makes a count for all cells, all neighbors. That's what it is.
Yeah, just counts to decide the next generation.
Right. I thought it was for a single cell. It's for all the cells. We then define one iteration of the game to be this, which says count all the neighbors. If there's exactly one or less than two, or wait, if it's less than two, if it's alive, that's what that is, sorry. If it's alive and there's less than two or more than three neighbors, it's dead. Otherwise, if it's dead and there's exactly three neighbors, it's alive. So this just iterates the game. It does one turn, I suppose, is a good way to put it. And then we have a function to display all this stuff, which is fine. And, whoop, wrong thing. Oh, I always forget you can do that. Right, so my computer actually crashed before I got here, which is why this isn't up. I was wondering about that. I black screened, which is an unusual thing where your video driver crashes and then doesn't recover. So not all the things I wanted to be open are open, and I apologize. So, as an objective comparison, before we see this functioning, I'll tell you it works. I hope you trust me. And I know that because I trust this guy, and I also watched it. Now, NumPy is cool. For the short version of it, it's very cool. NumPy does a lot of things differently with the array handling in Python. So, I think I showed you guys last time, I don't have it up anymore. Here it is. No, that was the thing I was just on. CV. This one. This is what I was looking for. So NumPy builds itself. Do I have a slide on this just so I'm keeping up with where I should be? There we go. So we have n-dimensional arrays, and it does some linear algebra. That was my takeaway from it when I've used it. And NumPy's description, according to their website, is powerful n-dimensional array objects, sophisticated broadcasting function, tools for integrating C, C++, and Fortran, which are compiled languages, which give us some speed when we need speed, and useful linear algebra, Fourier transformation, and random number capabilities. So Fourier transformation is a really cool thing that I think all of you know more about than I do. And since this is loaded, let's look at an example. So this was the Python version. I know the text is small. I'm just going to show you guys. This is the compute neighbors we saw. This is the show function to print it out. This is iterate, and then this just says show z for 4 iterations, play the game, and then show z again, where z is our initial field, which is defined at the very top. So we want to run this one. So our output here, no, I didn't. This here is the same as the initial state. No, it is not the same as the initial state, which is strange to me. Oh, this only shows a subset of the field. That's why. I don't know why they did that. That's silly. This is 2, 4. This is 6 elements, and this is only 4. And I don't know why this is only 4. But what they do is they show we have this glider shape here, and it moves down into the right one. We could iterate this more times, and we would end up with just a dead cell, a dead screen. If we change this to, again, I know this is small. I don't know how to change the text on this, and I'm not going to be using it for very long. But if I change it to 8, or let's just do 100 iterations, just for fun. If I do that, you'll see that, oh, we actually made a, that's not what I expected. So this glider that's here in this like J shape actually moved to a square of 4 ones in the corner, which a square of 4 ones, as we saw before, is stable. So it will continue to be like this no matter how many iterations we do. Not what I expected. I'm not an expert at the game though, so. Okay, so we've seen that it works in Python, and we've seen how big it was. So as a recap on that, there was exactly this much code in it. So NumPy lets us do some cool things, and this is where it gets exciting. So we have the same thing, except instead this time instead of declaring this as a 2D array like we were before, we say NP. So NumPy is defined as NP, so this is a NumPy array in this case. And what does that do differently? Well, it lets us do things like check the data types right here. We know that it's an int64. Int64 just means it's a 64-bit integer. That's some behind-the-scenes stuff. In this case, we're only ever going to store 1s and 0s in it, so it doesn't matter. We can look at the shape of our field, which is a 6x6 array. Now, in normal Python, you can do the length and the length of the first index, but it's not quite the same as this. We can do a different indexing. So in normal Python, you'd have to do z, close bracket, open bracket 5. This is just 0, 5. And this is where some of the magic comes in. We can do slicing, which I showed a little bit of slicing last week. And the important part is you create a range by using a colon operator. So this is pieces 1 through 5 and 1 through 5. Kind of gives us what we expected. It's a 4x4 matrix. NumPy likes to use a lot more linear algebra terminology. So instead of having a length, we have the number of axes and the something else. I forget what the other word they use is. I'm more used to conventional terminology, so you might hear me mix it. I'm going to try and use as much of the appropriate as I can, but I'm not used to carrying particularly. Sorry, trying to find the part this is exciting. Okay, this is cool. And why this is cool is a little weird. So you know that thing before we had where we counted all the subparts? I'll scroll up in here so it's the big text. This guy, this compute neighbors function, this whole thing, instead of that, with using NumPy libraries, we can do this. And what we say here is we've got np.zeros, z.shape, type is int. So this is saying I want a matrix of all zeros in the same shape as what we already have, same type of matrix, number of rows and columns, and I want it to be of type integers. Boom, we have a matrix of all zeros. Just works. And then this is the part that kind of blows my mind. I still have to wrap my head around this stuff.